Hello, I am Arindam Bhawal and I am going to explain about waveguides now. So yeah, let's begin. So let's start by discussing the content of today's discussion. First, we will start about the definition of waveguides, then the features, then types of waveguides. After that, we will talk about the advantages and disadvantages of it. Then we are gonna throw light on something on the applications of it, and lastly, we will conclude it. Let's begin. So, introduction. So what is a waveguide? So, waveguide is basically a pathway for waves to follow. We can say waveguide is a structure or a conduct that is used to guide and control the propagation of electromagnetic waves, typically in the microwave and optical frequency ranges. It is designed to confine and direct electromagnetic waves along a specific path, allowing for efficient transmission and minimizing losses. Waveguides can be made of different materials such as metal or dielectric substances like glass or plastic. Depending on the frequency range and application, they come in various shapes, including rectangle, circular, or planar configuration, each with its own advantages and operating characteristics. By confining and guiding the electromagnetic waves, waveguides provide several benefits, including reduced signal loss, high power handling capacity, improved signal integrity, and control over wave propagation. They are widely used in applications such as telecommunication, radar system, medical imaging, laser technology, and fiber optic communication system, among each others. So here are example of waveguides. The first one is a rectangular waveguide. The second one is a circular waveguide, and the waves are propagation in the way as shown by the arrow. Moving on to the next slide. Features. Some of the features that waveguide possesses includes confinement. Waveguides are designed to confine electromagnetic waves within their structures, preventing them from spreading out or into the surrounding medium. This confinement allows for controlled propagation along a specific path. Next, mode propagation. Waveguide supports different modes of wave propagation, such as transverse electric and transverse magnetic modes. These modes determine the distribution and polarization of electric and magnetic fields within the waveguides. Then is frequency selectivity. Waveguides are designed to operate within specific frequency ranges. The dimension and geometry of waveguide determine its cutoff frequency, which is lowest frequency that can propagate within the waveguide. The frequency selectivity allows for the transmission and control of signal within a specific frequency band. Next is losses and attenuation. While waveguides minimizes losses compared to other transmission medium, they still experience some level of attenuation. The material composition, surface quality, and other factors influence the amount of signal loss that occurs during wave propagation. Next feature involves the power handling capacity. Waveguides are capable of handling high power electromagnetic waves. Their design, material, and dimension are engineered to ensure efficient power transfer without excessive losses or damage to the waveguide structure. Next, we come to the waveguide geometry. Waveguide geometry come in different waveguides come in different geometries, such as rectangular, circular, as we seen in the previous figure, or in planar configuration. The choice of geometry depends on factors like frequency range, propagation, ease of fabrication, and specific application requirements. Boundary condition. Waveguide have specific boundary condition at the inner surfaces that dictate how electromagnetic waves interact with the waveguide walls. The boundary condition plays a crucial role in determining the allowed modes and behavior of the waves within the waveguide. Last but not the least, dispersion. Dispersion. Waveguides can exhibit dispersion when it is dependency of the wave's velocity on its frequency or wavelength. The dispersion can affect the signal quality and distortion of transmitted waves, and it is typically managed through careful waveguide design and material selection. Now let's talk about the principle of waveguides. Depending upon the frequency, waveguides can be constructed from either conductive or dielectric materials. Generally, the lower the frequency to be passed, the larger the waveguide is. For example, the natural wavelength, the earth form given by the dimension between the conductive ionosphere and ground, as well as the circumference at the medium altitude of earth, is resonant at 7.83 Hz. This is known as Schumann resonance. On the other hand, waveguides used in extremely high frequency EHF communication can be less than a millimeter in width. EM field configuration within the waveguide. In order to determine the EM field configuration within the waveguide, Maxwell's equation should be solved subject to appropriate boundary condition at the walls of the guide. Such solution give rise to a number of field configuration. Each configuration is known as a mode. Moving to the next slide, let's talk about some of the advantages. Some of the advantages include low signal loss. Waveguide exhibit lower signal loss compared to other transmission medium, such as coaxial cables or open space propagation. The confined nature of waveguides minimize radiation and external interference, resulting in higher signal integrity and reduced losses. High power handling. Waveguides are capable of handling high power electromagnetic waves without significant degradation. The confined structure of waveguides allows for efficient energy transfer and reduces the risk of power loss due to radiation or resistance, making them suitable in high power application. For high power application, better electromagnetic isolation. Waveguides provide excellent electromagnetic isolation, minimizing interference and cross-link between transmission paths. This feature is crucial in applications where multiple signals need to be transmitted simultaneously without interfering with each other. Controlled wave propagation. Waveguides offer precise control over the direction, shape, and characteristic of wave propagation. Wave propagation. By carefully designing the waveguide geometry and dimension, engineers can guide and manipulate electromagnetic waves along desired paths, enabling efficient signal routing and beam shaping. Frequency selectivity. Waveguides can be designed to operate within specific frequency ranges, providing frequency selectivity. This allows for the transmission and control of signals within desired frequency bands, enabling efficient filtering and separation of different signals. Reduce electromagnetic interference. The confined nature of electromagnetic waveguides helps to contain and schedule electromagnetic waves, reducing the risk of electromagnetic interference with other sensitive electronic devices and systems. This makes waveguides suitable for applications where EMI needs to be minimized. Compact size and integration. Waveguides can be designed to be compact and integrated into smaller devices or systems. The feature is particularly beneficial in applications where space is limited, where minimization of requirement. Wide frequency range. Waveguides can operate across wide range of frequencies, from microwave to optical frequencies. The versatility allows them to be used in various applications spanning telecommunication, radar, medical imaging, and many more. Now, coming to disadvantages. Firstly, size and weight. Waveguides, especially those designed for lower frequency, can be bulky and relatively heavy compared to other transmission medium like coaxial cables or wireless transmission. They can pose challenges in terms of insulation, space, requirements, and portability. Cost and compatibility. The design, fabrication, and assembly of waveguides can be more complex and costly compared to other transmission medium. Waveguides often require precise uh, manufac- manu- manufacturing techniques and materials, leading to higher production costs. Limited bending and flexibility. Waveguides have limited flexibility and bending capability compared to other transmission medium like cables. These are generally rigid structure and may require careful routing and insulation to avoid excessive bending or sharp turns, which may affect their performance. Frequency dependency. Different waveguide designs are optimized for specific frequency ranges, and their performance may deteriorate significantly outside those ranges. The frequency dependency can limit their usability in applications requiring wideband and broadband signal transmissions. Higher propagation losses at high frequencies. Waveguides tend to have higher propagation losses at higher frequencies, particularly microwave and millimeter wave ranges. As frequency increases, waveguide dimensions become smaller, resulting in increased energy losses due to factors such as conductor resistance and radiation. Fabrication challenges. The fabrication of waveguides, especially at higher frequencies or optical ranges, can be technically demanding. Achieving precise dimensions, smooth inner surfaces, and uniform material properties can pose challenges, affecting the overall performance and cost of the waveguide propagation. The limited signal access. Accessing the signal with a waveguide for testing, monitoring, or tapping purposes can be more challenging compared to the transmission mediums. Waveguide structures typically require specialized connectors or coupling techniques, adding complexity to signal access and integration of other components. Environmental selectivity. Waveguides can be sensitive to environmental factors such as temperature, humidity, and mechanical stress. Changes in this condition can affect the performance and stability of waveguides based system, requiring careful design considerations and protective measures. With this, I'd like to conclude. I hope you, I hope you had a good day, and thank you. Thank you.